what I'm going to essentially do to you today is help you learn the art of counting starting from scratch. We'll not do anything high funda today, nothing big, but very basic things. Perhaps the only objective of the class today is to help you learn what and means and what or means. This is all that I want to do in a very simple manner. I don't want to dump extreme amount of sophistication right away. Simple things, right? Now, when I attempt to initiate combinatorics or the art and science of counting, then we must take it from ground up, in the sense, how you would have counted if you were not familiar with any tools related to counting, and then how the tools intervene and help you count more effectively, right? You can always do counting. One, you can do it without the tools, that would be crude. Two, you would use some tools that you would learn. But then, a word of caution while I'm teaching you combinatorics. The word of caution is, even though we learned some tools formally, but the informal essence of counting should always be kept in mind. We should never get extremely formal with the business of counting. We should make ourselves available to informal ways of counting, absolutely related to your natural instincts of counting, right? Now, just to illustrate something very simple. Suppose I had a coin, call it C, right? And I toss that coin, right? If I toss that coin, what are the various possibilities? Heads or tails. H denotes head, T denotes tail, right? Two outcomes if I tossed a coin, a head or a tail, right? So, two outcomes. In this case, so easy to count, 1 plus 1, right? Suppose we had two coins, C1, C2. These were two coins. And I had to flip the coins. Right? Then, one possibility is, I flip the coins simultaneously. And now I'm trying to judge the outcomes, right? One is, both heads, C1H, C2H, head, head. Both tail, TT, right? The first head, the second one tail, or tail, head, right? So the outcomes are this, or this, or this, or this. These are the various outcomes, right? So then, 1, 2, 3, 4. 4 outcomes, right? This was small in magnitude, so easy to count, right? Suppose there were 3 coins. 3 coins, C1, C2, C3. Now, see, the number of all this we have done manually right now. This was all done very manually, right? Now again, if I had to do things manually to discover the total number of possible outcomes of tossing 3 coins simultaneously, then one outcome would be H, 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 T, 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 H, T, 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 H, and And we'll have to build it up. Do you realize that it's getting uglier? To do this manual count now, 1, 2, 3, etc. We've just moved from 1 to 2, and the third one seems like an impediment. It looks thorny, right? Not liking it. It's getting very manual now, right? Now, if there were 4 coins, and I had to do a manual count for 4 coins, C1, C2, C3, C4, that'll get even uglier, right? So then, when counting is related to smaller magnitudes, it's not an issue. You could deploy manual means to count. But then when the total count grows, then deploying manual means is ineffective. It will lead to waste of time and effort, right? And that's why we are into the business of counting, professionally counting, counting with sophistication, with the aid of some tools. We're wanting to build it up. But while we are building it up from ground upwards, we should keep track of the basics. In the sense, we should not forget the formation of these tools, which is the foundation. The formation of these tools, the formation of sophistication that has led to this entire business of counting should be kept intact, because some of the best problems in combinatorics will not involve the tools that I teach you, will not involve the tools that are there in books, will not involve any semblance of formal learning of the subject. It will involve an informal, articulate sense of the subject. That is important. So, keeping the informal aspect of the subject is more important than simply learning the formal aspects blindfolded, right? Bear this in mind. Now, without even teaching you anything, without actually teaching you anything, what I want to do is, I want to do some informal counts. Okay. And then we'll get into a more formal approach towards things. But one of the things that I would expect you to have known by this time is one notation called the factorial notation. Now, just in case you're not absolutely familiar with the factorial notation, I'll give you a quick crasher on factorial. If I have a natural number n, then n factorial is actually 1 into 2 into 3 into 4 to n. That's factorial n. Product of the first n natural numbers. That's factorial n. 1 into 2 into 3 into 4 into n. This could also be written as 1 into 2 into 3 n minus 1 into n. It could be written like this also, rewritten like this, right? But 1 into 2 into 3 up to n minus 1 is by definition n minus 1 factorial. So that means n factorial is n minus 1 factorial into n. This is true for all n, right? As a special case. So 1 factorial would be 1, 2 factorial would be 2, 3 factorial would be 1 into 2 into 3, 6, 4 factorial would be 24, and so on and so forth, right? Give me a moment, I'll explain. Put n equal to 1 on both sides here. Put n equal to 1 on both sides here, you get 1 factorial equal to 0 factorial into 1. So then bring this 1 here, that by definition gives me 0 factorial equal to 1. 0 factorial equal to 1. Put n equal to 1 on both sides. So 1 factorial, which is 1, is 0 factorial into 1. So 0 factorial is 1. In fact, let me tell you, by the time you mature towards the end of class 12, I will also be able to deliver to you factorials of fractions. I'll be able to tell you what it means, factorial 5 by 2. There are functions that define. So we will extend. See, this is how we start with the whole business, but then we extend the wings and make them look very general. So we'll make it very general, but then when we start learning the subject, we stay confined. For the moment, we'll stay confined, but we'll generalize things and make them look better and better as we chug along. Okay. Now, so this bit I expect you to have known, the factorial notation. Now, let's start to count without having learnt any tools of counting. Let's start to learn without having learnt any tools of counting. And then there would be a thin line where we'll migrate from an informal to a formal approach. Right? So let's keep ourselves mentally available for that migration as and when it comes. But ab initio, I'm just going to give to you some very informal basic treatment of the whole thing, which requires only logic. It doesn't require any formal approach. Okay. Now, like I said, the coin problem, you know. So 1 was all right, 2 was also all right, coin 1 and coin 2, for example, very simple. It was like, when I flipped the coin C1, there were 2 possibilities for C1. It would either give me a head or it would give me a tail, right? So 2 possibilities. When I flipped C2, then there were again 2 possibilities. It would either create a head or it would create a tail. So 2 possibilities. And when I flipped C1 and C2, then it would be like, let's say C1 was head, at some, see, C1 could have been head or a tail. So if C1 was head, then for a head, C2 could be either a head or a tail. If C1 was head, C2 could be head or a tail. If C1 was tail, then C2 again could either be a head or a tail, right? So that makes it 2 and 2, 4 options. That means the way the tree works, is number of ways, number of outcomes related to C1 followed by number of outcomes related to C2. So 2 outcomes related to C1 and 2 outcomes related to C2. Therefore, number of outcomes related to C1 and C2 would be 2 into 2. That makes it 4. Number of outcomes related to C1 and C2 would be 2 into 2. That makes it 4. Right? Similarly, if I am flipping 3 coins, C1, C2, C3, then the total number of options produced would be, C1 would give me 2 possible options. It would be a head or a tail. Following a head or a tail, there would be 2 options for C2, head or a tail. C2, head or a tail, 1 or 1. So whenever I say or, I am actually adding head or a tail. That means 2. 1, 1, 2. So the moment it's a or, fundamentally believe, intrinsically believe that it's a case of addition. Right? C1 and C2. So when it's and, you are actually multiplying. And then C3, you are again multiplying. So that makes it 8 possible outcomes when C1, C2, C3 are tossed. Yes or no? Yes. Right? Can I wrap this off? Now, again, not to bog you down with formal understanding right away, let's look at this bunch of problems titled ground state. Bunch of problems titled ground state. Some of these, just to get a mental feel for counting, ab initio, let's start doing it together. No rocket science, but we'll just use our understanding of and, or, and or. Right? That's what we'll do. Fundamentally, realizing that if it's and, if there is an event A and an event B, then event A and event B will take place with multiplication. Suppose there is an event A followed by an event B. That means if it's followed by an event B, that means it's event A and event B. And event B. That means it's not or, event A and event B. And if event A takes place in small a ways, and if event B takes place in small b ways, then the number of ways in which the event AB takes place, when I say AB means A and B. A and B. I will designate A and B by A intersection B. Intersection is and. Intersection is and. Mathematically, this would mean and. A and B. If I say A union B, union would mean or. Elements that belong to A or B, isn't it? That's union. Intersection mathematically would designate and union would designate or, right? So this would mean or. Now, if the event A occurs in small a ways, event B occurs in small b ways, then the event A and B, AB, will occur in AB ways. In AB ways. Right? Assuming that the events are not interfering with each other. Events are not interfering. I mean, that means, these ways of occurrence of A have nothing to do with these ways of occurrence of B. That means, say for example, you are at my class right now. Okay? And that's your home. Okay? The way you go home is from the class, let's say you go to Ultadanga. Right? And there are, say, 3 ways you could have gone to Ultadanga. There are 3 ways you could have gone to Ultadanga from the class. Right? So that's event A. Going to Ultadanga is event A. And then from Ultadanga to home, say suppose there are 4 ways. 4 ways. These are 3 ways and these are 4 ways. So this is event A going from class to Ultadanga. And these are 4 ways going from Ultadanga to home, right? 2 events. In order to reach home, let's say these are necessary events, A and B. This is event A, those that lead you to Ultadanga, and then event B that lead you from Ultadanga to home. Those are 4 ways. And in order that you want to reach home, these are indispensable. And that the way that you select from going from class to Ultadanga, they have nothing to do. They don't interfere with the ways that you select from going from Ultadanga to home. For example, you take bus X from class to Ultadanga, right? And from Ultadanga to home, let's say you take an auto. Say an auto Y. Now this auto Y will not tell you that, well, in order that I give you a ride from Ultadanga to home, you couldn't have traveled by bus X. They don't interfere with each other's operations. That's what I mean, right? You know what I'm saying? And if that happens, then you can multiply the 2. Therefore, the number of ways you can go from class to home would be number of ways in which event A, which is going from class to Ultadanga, into number of ways in which event B could take place, which is about going from Ultadanga to home. So that makes it 12 ways. 12 ways. Now, again, tell me one thing. If you have already gone from class to Ultadanga, why do you want to repeat this event? No, that's what. Therefore, obviously, you're not repeating event A. A and B means event A is being executed once and event B is being executed once. Otherwise, if that is allowed, then, well, you want to repeat this event. That means you again want to come from Ultadanga to class. So 3 ways into 3 ways, 9 ways. And then again into 3 ways, 27 ways. Now, you want to do that. You don't want to shuttle between class and Ulta Danga uselessly, right? Until and unless you have other ulterior motives, right? So when I say A and B means the event A executed once followed by a single execution of event B. That is assumed logically, okay? So A and B would take place in number of ways in which A could be done into number of ways in which B could be done. So this business of AND is about multiplying. Assume that the two events have no bearing on each other, right? Now, or, when I talk of or, right? So when it's or, say you want to have a party and there are 5 families that you know, say F1, F2, F3, F4 and F5. There are 5 families you know. Five families you know. And what you want to do is, you want to invite from one of the families. You want to select only one family out of these 5 to be in the party. You want only one family to be in the party, right? That means you either want members of family 1, F1, or you want members of family 2, or you want members of family 3, or you want members of family 4, or you want members of family 5. So then, in how many ways could you invite people? 5. Just 5 ways, right? Then it's a case of or. This, or this, or this, or this, or this. There is only one way of inviting members from family 1, F1. There is only one way of inviting members from family 2, F2. 2 ways. Then one more way, just one way from inviting members from family 3, 4, 5. So there are 1 plus 1 plus 1 plus 1 plus 1. So that makes it 5 ways of having your party go through, right? So this entire thing about or is essentially addition, intrinsically addition. So if there is an event A that takes place in small a ways, and there is an event B that takes place in small b ways, then the number of ways in which A or B takes place is A plus B. Number of ways in which A or B takes place is A plus B. So whenever there is an or, intrinsically it's about addition, and intrinsically is about multiplication, right? So that's the fundamental principle, and you know, I'm sure even if it was not told to you, you would have got it all by yourself, right? So because this is what you've been doing. I mean, you already knew that if there were 3 ways of going from here to Ulta Danga and 4 ways of going from Ulta Danga to home, there would be 3 into 4, 12 ways of going from class to Ulta Danga. So this actually did not require a formal treatment, right? So this aspect of combinatorics, from where we are going to build it up, is the objective of the class, right? I'm not going to do any heavyweight combinatorics today, but then let me set up the foundation in terms of dealing with the whole thing from first principles rather than dealing it with the help of too many formulas and results. Okay.
So
now
suppose that I can invite as many family from this 5, means either 5 or 4 or
let me give you enough so that you can handle that also, right? Let's, in the first place, go past these rudiments and then take life head on from that point onwards. All right. So refer to this bunch of extremely simple but instructive situations in a sheet titled Ground State, which would build our foundation of the fundamental principles of counting, which would tell us the difference between and or, difference between and or, right? That is what we want to know. So the first situation, now I'm not interested in the answer, I just want you to get a feel for and or. That's all that I want you. The answer is not important because these are very simple situations, but they are required. You know, down the line, this is where you'll make mistakes. I can tell you that. If I teach you formulas and results, you'll remember those, but you'll goof up with very simple elements. That's where you'll goof up. Therefore, even though very simple, they will drive home a lot of instruction. Okay. So now, in this sheet titled Ground State, where all that we are trying to do is familiarize ourselves with the very basic fundamental principles of counting. You already are familiar. Purohit, when I'm talking, you need to just listen to me or talk to me if there is a doubt. Otherwise, don't swivel your head unnecessarily. Okay? So then, a man has 3 jackets. Man has 3 jackets. Say J1, J2, J3. These are the 3 jackets he has. And has 10 shirts. Call these shirts S1, S2, S10. These are the shirts that he has. And 5 pairs of slacks. 5 pairs of slacks. Let me call these slacks P1, P2, P5. These are 5 pairs of slacks that he has. How many different outfits a man could make? I mean, we're assuming that every outfit would comprise of 1 jacket, 1 shirt, and 1 slack. He's not going to wear 2 jackets. He's not going to wear 3 shirts. He's not going to wear 4 slacks, right? So those are logical assumptions. Although you could argue saying, no sir, what if he wears 2 jackets and 3 shirts and 2 slacks? No, that's, you have to be a madman to do that. I will not stop you from doing that, but while solving these problems, we will stay within the jurisdiction of normal human behavior. Okay? So, now, to create an outfit would have to be a jacket and a shirt and a slack. A jacket and a shirt and a slack. This is and, right? A jacket can be worn in 3 ways because he could wear, it's not like 1 jacket worn in 3 ways. It's like 3 jackets, each being worn in 1 way. Right? That's what I mean. I mean, you're not going to say, well, again, departure from normal human behavior, you can wear a jacket like this or you could wear a jacket like this. That's possible, but that's mad behavior. Right? Then you want to first go for some treatment to Rachi. Okay. So, again, a jacket, 3 jackets available, he could wear any one of them. So a jacket could be worn in 3 ways, right? 3 ways of wearing 1 jacket the right way. Okay. And then a shirt, and means multiply. And a shirt, 10 shirts, he'll wear 1 shirt. Don't tell me it's so cold he's wearing 3 shirts. Alright, so 1 shirt, out of 10 he can wear 1 in 10 ways, because he could wear, again, why 10? Either S1 or S2 or S3 or S4. Realize moment there is or, we are adding. So 10 ways of choosing a shirt from his collection, right? And then one pair of slacks. He has 5 pairs. He wants to select one to wear. So that he can do out of 5 in 5 ways. So that makes it 150 different ways in which he could wear a outfit, right? Of course, 150 possible outfits. Once we mature, we'll deploy conditions. In the sense, we'll say, all right, you know, he's not going to wear a red jacket with a green shirt. So then that'll limit the number of ways in which he could wear outfits. But that would be conditional adding. That'll be conditional adding. But let's get past unconditional adding before we migrate into the conditional ones. All right. Okay. So that's one. So this is the situation, and the number of ways in which he could create outfits is number of ways in which he could wear a jacket, into number of ways he could wear a shirt, into number of ways he could wear a pair of slacks. So that makes it 150 possibilities, 150 outfits therefore. Simple, right? Okay, let's look at the next one. Now, the number of ways in which four people could be accommodated in 3 different chairs. We'll assume that, right? There are 4 people and 3 chairs. There are 4 people and 3 chairs. We want to find the number of ways in which the 4 people could be accommodated in 3 chairs. In the sense, obviously, it's about one person per chair. There would be one person left out. So it's like 3 chairs, C1, C2, C3. What effectively the problem says is, given 3 chairs, C1, C2, C3, in how many ways can you fill up these 3 chairs out of 4 people? That's what it says. The problem actually says that, well, there are 3 chairs, call them C1, C2, C3 if you like, and in these 3 chairs, I don't want to leave them vacant, and I want to accommodate exactly one person in each chair. I mean, you know, it's possible that one of them could be him and one of them could be him. Then both could be accommodated in the single chair. Difficult though. But we'll assume that, you know, one person per chair, one chair, and no chair goes vacant. Because then that will become conditional. The simple problem is 3 chairs, C1, C2, C3, and I want to fill up these 3 chairs out of any one of the 3 people. That's an equivalent problem. You know what I'm saying? Okay. So the first chair, call it C1, that could be occupied by any one of the 4 people. These are the 4 people. P1, P2, P3, P4. These are the 4 people. The first chair could be occupied in 4 ways. It could be occupied either by P1 or by P2 or by P3 or by P4. Realize that moment I'm saying or, I'm adding 1 plus 1 plus 1 plus 1. I've actually added without knowing that, well, I've actually added. It's so 4 ways in which I could have filled up chair C1. Now, so one of the 4 people would have got consumed in filling C1. Now, how many people am I left? So the event of filling C1, see, there are 3 events. Event of filling C1 and event of filling C2 and event of filling C3. 3 events. So equivalently, what is it that I'm dealing with? I'm trying to find the number of ways in which the first event of filling C1 and the second event of filling C2 and the third event of filling C3 could take place. That's what I'm trying to find, right? Now, event of filling C1 can take place in 4 ways. Either P1 or P2 or P3 or P4 could oblige, right? Now, event of filling C2. That's the second event. And it's about and. Because you don't say filling C1 or filling C2. You are saying filling C1 and filling C2. So and filling C2, number of ways in which C2 could then be filled. One of them have got consumed. We are left with 3 people, and any one of the 3 could fill up C2. So the second event, that of filling C2, can take place in 3 ways. Then and the event of filling up C3. So 2 of these have got consumed. 2 of these have got consumed, 2 remain. Now any one of the remaining 2 could occupy C3, and that can take place in 2 ways. So event of filling C1 and C2 and C3, that makes it 24. It will get, No, but I have not even taught factorial or anything. In the sense, I have taught factorial, but how do you know factorial, 4 factorial? Its fundamental principle of counting is all that I am deploying, right? Nothing else. Forget the NP3 and yes. You will, no. People will sit in the chair will not sit in the people. Right? So again, let's go by that. She's saying, let's have the people and place the chairs on them. We will not do that, right? That's the logic. So don't do that. Okay. Simple, right? Got it? And the problem will get conditional as we mature. In the sense, we'll have ways of filling C1, C2, C3 where P1 and P2 are goddamn great friends, and they say, we'll always be together, or we will not fill up these. So in a selection, they'll say, okay, P1 and P2 have to be there together, or both are not there. Either both are there or both are not there. If both are there, they sit. If both are not there, they go to Inox. Right? They'll find a pair of chairs where they could sit together. All right, so simple, right? No rocket science? Similarly, so essentially just get a feel for the and the ors. That's all today. If you do that, then that's good enough. Okay, so now the next one. So now the next one is about thieves. So we have in a store doors and windows. Normal people would want to enter and leave through the door only, but a thief has an option, right? He'll prefer, in most cases, to enter through the window, right? Why so? You know what? I'm so surprised that the moment you pass some frivolous remarks like this, you are not scared of my reaction, because you know that these impromptu reactions could be very damaging to your psyche. All right. So all that I want to say is, while the class is on, keep your psyche protected from my attacks. Right? Even though just before pujas, I want to keep you smiling broadly, but until and unless you instigate me into extraneous effects, right? Okay. Now here, Bell mujhe maar. I was not saying anything. By the way, all these days, your poor kids left unattended, and you were having some fun and frolic in Bombay. Why did you do that? You should have taken care. This fellow had to take care of that many kids. Okay. All right. So here we have a case. It's difficult to draw 8 doors and how many windows? God knows, 12 windows. So I'll just say there are 8 doors and 12 windows. My God. Quite a few 8 doors. Imagine. 8 doors and 12 windows in a store. In how many ways a thief can enter the shop? Well, he has an option. Logically, a normal man would enter the shop only in 8 ways, because he will use only the door for entry purpose. But the thief can enter the store either through the door or through the window. Door or window. Realize that. So then, so it's a case of or. So he enters either through the door or the window, because he's a thief. Right? So then, number of ways in which he could enter through the doors? 8. Or number of ways in which he could enter through the windows? 12. 20 ways he could enter the store. 20 ways he could enter the store. Right? The problem can get conditional if the thief had preferences. Right? In how many ways can the thief rob the shop? By entering through a window and leaving through a door. Okay? Entering through a window. So he enters a window. Event 1. He's entering the store through a window. That's event 1. Right? Event 1 is his entering through the window. That takes place in 12 ways. He enters the store in 12 ways because he can enter only through the window. Alright. But then now he has access to the door because he could unlatch the door. Right? So he says, Itna mal leke, how can I leave through the window? I would have to use the door. Right? He says, I will have to use the door. With so much of stuff in my hand. The windows are too small. Right? So he says, I will enter through event 1. I will enter through the window. But I will leave through the door. So he enters in 12 ways. And because he doesn't want to get stuck up there, so he has to leave also, right? So event 2 is important, that of this fellow leaving the store, and he chooses to leave through the door. He leaves the store in 8 ways. So entering 12 and leaving 8. So that makes it 96 ways in which he could rob the store. 96 ways in which he could rob the store. Choto kato chor hole ki hobe? If there is a small thief, he'll say, all right, I don't want to carry too much. I will enter through the window and leave through the window. So 12 ways in which he could enter into 12 ways in which he could leave. So that will make it 144. No, point is that all of them will enter together through the same window. They're thin like him, yaar. Okay. Simple, right? Nothing difficult about it. Now, problem 4. A department in an organization, a certain department in an organization has a certain number of male employees and a certain number of female employees. So the department has 17 male employees and 15 female employees. And what they want to do is, an employee is required. In how many ways can an employee, that means one employee, be chosen for an annual general meeting? So from this department we need one representative. From this department that contains 17 males and 15 females, we need one representative for the AGM, annual general meeting. So in how many ways can that be done? So that one person would either be selected out of 17 males or 15 females. So out of these 17 males, in how many ways can I select one representative? 17 ways, right? So 17 ways of selecting a representative from this, or 15 ways of selecting one representative from this. So that makes it 32 ways in all. So to select a representative, the number of ways in which a representative could be selected from these is this, one from here or one from there, right? One from here could be selected in 17 ways, one from there could be selected in 15 ways. That makes it 32 in all, right? Now, to keep a balance, they decide that the AGM must maintain sex ratios. So they say, all right, we need from every department a male and a female, right? So that there is equal responsibility. So they say, all right, so a male and a female this time. So one person to be selected from here and one person to be selected from there, right? So a male and a female from this department and a female to be selected in 17 ways. A male could be selected into 15 ways, a female could be selected. So 17 into 15 ways. Okay, 255. 255 ways. Right? Yes or no? Yes, sir. Very good. Now, it's going smooth, right, so far? Okay. Now, how many words with or without meaning of 3 distinct letters of English alphabets are there? 3 distinct letters. So, which means L1, L2, L3. So they say this is a word to be constituted where L1, L2 and L3 are distinct letters of English, distinct letters, right? So it's about having 3 spaces. L1, L2 and L3. And filling up these spaces with the 26 alphabets, with any one of the 26 alphabets, right? Where the alphabets selected for L1, L2, L3 all have to be distinct. All have to be distinct alphabets to be selected for L1, L2, L3. And the word may not make sense at all. That's all right, right? Half the words anyways don't make sense. I'll tell you that also. So if there is L1, L2, L3 and L3, L1, L2 and L3, these are essentially, mentally I am imagining 3 spaces. Mentally I am imagining 3 spaces to be filled up by these English alphabets such that L1, L2, L3 are all different. So then, let me start with L1. The space allocated to L1 could be filled up in 26 ways, 26 alphabets, so 26 ways. Now, after I have used an alphabet for L1, I am left with how many? 25. So, any one of the remaining 25 could be used up for filling L2. And then, I have used up 2 alphabets, one for L1, one for L2. You know what? Go and take a wash. What's your name? Swapnil, go and take a wash, please. Sitting right under my nose, and you know, if you know it all, I'll let you go. You can go. Then, no, it doesn't seem there is a problem with the eye, it looked different. Go and take a wash then. So then, L1 filled up in 26 ways, and L2 in 25 ways, and then I have used up 2 alphabets to fill up L1 and L2. I am left with how many? 24. So L3 could be filled up in 24 ways. So if L1, L2, L3 are all distinct, then the number of 3-letter words, where all the letters are distinct would be these many. All letters distinct. No, I'm not don't worry. I mean, I'm not interested in the product. I know all of you can count, multiply. Wait, I'm coming to that. If say I have a bag in which there are infinity of A's available, large number of A's, and I have a bag in which there are large number of B's available. And if I have a bag in which there are large number of C's available, a bag in which there are large number of Z's available, right? And I'm allowed to pick any number of A's, any number of B's, any number of C's, any number of D's, any number of Z's, and allocate them to these spaces. That means I'm saying, okay, I have access to large number of A's, I can use any number of A's. I have access to any number of B's, I can use any number of B's. That means I could fill up L1, L2, L3 with the same letters also. Suppose I am allowed that. That means if L1 has L2, L3 have no limitations. That means the number of ways in which I could fill L2 does not depend on what I have used for L1. Number of ways in which I fill up L3 does not depend on what I have consumed for L1, L2. That means I am allowing repetition of letters. If I am allowing repetition of letters in these three spaces designated L1, L2, L3, then, so this is without repetition. If I allow repetition, then L1 could be filled up in 26 ways. I could use any one of these. L2 could be used in 26 ways, L3 in 26 ways. So that makes it 26 Q ways if repetition is allowed. Right? Now, see, can I have this on? One thing that you must realize when I am doing this, one very basic thing that you must realize. Can I wipe this off? When I'm filling up spaces, I'm inadvertently doing one thing. I do not know if it has missed your attention or not, but while filling up spaces, I'm certainly carrying out one thing. I'll tell you what. See, in doing this 26 into 25 into 24, these many counts, you know, these many words created out of 3 letters, 3-letter words created. One thing that is happening is, say if a word of the kind PQR has come. If a word in this count, you know how many, whatever this 15,600 you said, right? So in 15,600 such words, suppose one word is PQR. Suppose one of the words is PQR, then you will also expect a word QRP to come. You would also expect a word QRP to come. You would also expect a word RPQ to come, and so on and so forth. You would expect all these words to come. That means in filling up spaces, it says PQR is different from QRP, is different from RPQ, and so on and so forth. That means it says the order in which the letters come is built into this count. The order in which these letters are coming is built into this count. See, for example, 1, 2, 3, there is 3 added to this. That there is 3 built into this because of different arrangements of PQR. Actually, you will find that PQR could be arranged in 6 ways. You can check that manually right now. There are 6 ways. There are 6 ways PQR could be filled up. Yes, absolutely. In the sense, you know, manually, just doing it manually to begin with. Say, you can have P here, Q and R here, or R and Q here. So with P at the first place, there are 2 ways of filling the remaining 2 spaces. You could either have a QR or you could have a RQ. So with P in the first place, you could have 2 ways of filling up the remaining 2 spaces. You could have had Q in the first place, and then you could fill the remaining 2 spaces in 2 ways. You could have had R in the first place, and you could have filled up the remaining 2 spaces in 2 ways. It could either be PQ or it could be QP. So it could be QP or PQ 2 ways. Now, so a set of letters PQR, what is the count that they have contributed to 15,600? They have contributed 6. They have contributed 6. In this 15,600, a PQR collection has appeared thrice in different orders, has appeared six times, has appeared six times in different ways. With P in the first place, QR, RQ. With Q in the first place, RP, PR. With R in the first place, PQ, QP. So 6 ways. That means, see, it would, if I have used PQR, 3 letters to constitute the word L1, L2, L3, then it would either be P coming in the first place, or Q coming in the first place, or R coming in the first place. So when it's P, 2, or Q, 2, or R, 2. So that's why I add 2 plus 2 plus 2. That makes it 6 ways. 6 ways. Do you all understand this? So every set of 3 letters, distinct letters, every set of 3 distinct letters that have been consumed towards constituting a word L1, L2, L3, towards constituting a word L1, L2, L3, that set of 3 letters has appeared in different arrangements, 6 times, 6 times. Do you understand this? Yes or no? Right? Yes, that has appeared 6 times. Every time 3 letters are selected and they are arranged in these 3 spaces, there have been 6 possibilities that have emerged. And that is because the order in which the letters are appearing here, when I am filling up spaces, the order is being built into it. That means which one coming first, which one coming next. It's not like it has looked upon PQR the same as QRP. It's not looked upon the same as RPQ. All these 2 and 2 and 2, 6 ways are looked upon as different, because the order in which PQR appear in this filling up spaces is different. So filling up spaces builds in order always. If you fill up spaces, it will build in orders. It will always build up an order. The manner in which one element comes after another element is built into filling up spaces. This you must remember. The order in which the elements appear will be built into it the moment I look at a pro forma related to filling up spaces. The moment I boil down to filling up spaces, the order will get built in. This is important to understand. Very simple, but again, when people grow, they goof up in this only. Okay? Now, that's exactly what I was coming to. You are a smart girl. Very good. See, again, so they were, what we started with, what, 26 letters? What we started with was 26 letters, right? And what did we do by filling up these spaces? We created 3-letter words. We created 3-letter words. And in a word, the order in which letters come in is important. I mean, ON is not the same as NO. Right? It's the same letters, but they mean different. They mean different things. So, the moment it's about creating words, then the order in which the letters appear will become important. So, the number of ways in which I created 3-letter words is about filling up these 3 spaces, which I could do in like 26 into 25 into 24, and like I said, I built an inherent order in this. Clear? But if someone told you, just select 3 letters distinct, 3 letters distinct from 26 available. Just selecting 3 letters. That means, yes, absolutely. That means PQR and PRQ will be the same. QRP and QPR will be the same. RPQ and RQP will be the same. That means for every set of 3 letters PQR, the 6 that you have created out of this, in which the order was prevalent, the order was important, will in our selection become 1/6. Because then I could just say PQR. That is 1/6 of these many, that's 1/6 of these many, yes or no? Yes, so if I say just select 3 letters, then what I do is, all these 6 are there in this count. In this count, all these 6 are there, for example, PQR. And for every set, there are 6, but only 1 is important. In the selection, only 1 is important. That means, if there are 6 for every 3, right? Every time I fill up this, there are 6 arrangements that I get 6 arrangements. But in selection, there is only 1 arrangement that is important. That means, only 1/6 of this is important if it's about selection. Only 1/6 of this would be important in as far as selection is concerned. Yes or no? Yes, sir. Because I would not want to distinguish between PQR, PRQ, QPR, QRP, RPQ, RQP. I would regard all of them the same. It's about selecting. Therefore, for every 6, there would be only 1 that would be about selection. That means, when I would say select 3, then it would be 1/6 of this. That would be 1/6 of this. That means that will be 15,600 divided by 6. Yes or no? Yes or no? Yes, sir. Right? Now this is called suppression of the count. That means I have suppressed the count by dividing by 6 to get the required. Suppress and conquer. This was suppression and conquering. You understand what I'm saying? Yes, we have suppressed by 6 and we have conquered. Right? Now just to build this a little more. So this would be the number of ways in which 3 letters could be selected. This would be the number of ways in which 3-letter words could be built. But this would be divided by 6 is like suppressing the additional counts. See, out of these 6, only 1 is relevant. Others are only add-ons. That's not required in the selection. So only 1/6 of the count is important. 1/6 of this count would be important in as far as selecting 3 letters is concerned. Are you all there with me or not on this? Yes. Now, suppose, can I wipe this off? Yes, sir. So filling up spaces, cardinality is building order. If the order is not important, then you suppress the count by dividing by a certain number. Right? If it's about selecting only and the order is irrelevant. Right? I mean, if you are selecting, let's say, out of 26 students, 3 students for a march past, then the order is important. Then it's okay to fill up spaces. Right? But if you are selecting 3 students to go for a science contest, then the order is not important, right? They'll not go to the contest marching past, right? Even if they do, it does not matter. So all that matters is whether you have selected Suresh, Ram and Vishal or Ram, Vishal and Suresh. It's going to be the same, right? So there you will have to suppress the count. Even if you ended up filling the spaces and counted, you will have to suppress that count by a suitable number to get the required, right? Now, one thing that you must understand, so far so good, right? You're all in sync with me. Okay, very good. Suppose there are, say, R people. And whatever I will say of people will also be true of donkeys. So it's just that I'm using people for counting. We could have used donkeys to count also. So suppose there are R people. Obviously, whenever I say R people means they're all different, right? So I don't have to specify and say are different people. There are people obviously different. That's the reason I'm not using inanimate objects. I mean, I could have said are coins. You know, they could be identical, right? But when I say are people, obviously they have to be different. That's the reason I choose to use are people for helping us learn how to count. So suppose there are R people and I want to arrange all of them. for a march past. All selected. You can select all of them in only one way, isn't it? You can select all of them in only one way. You don't have to use formulas to determine how many ways. You can select 20 people out of 20 available. There is only one way, right? Okay, so out of R people, I select all of them. That's only one way in which I could do. The next that I do is, I want to arrange them in a row, let's say for a march past or whatever. Okay, so now I create R spaces. So the filling up spaces will build the order. So if I have to arrange them where the order becomes important, then it's okay to model around filling up spaces. It's okay to model around filling up spaces. So R people, and say these are R spaces. R spaces. R people and R spaces. I want to fill up these R spaces with R people, right? Are you lost? Zombied? Right? R spaces with R people. So now the first space can be filled up in how many ways? R ways. R ways of filling up the first space. So this is space 1, this is space 2, this is space 3, space 4, space R. R ways. Hey, one thing let me tell you, those of you, who kind of getting out of this because they think they know it all, I can tell you that if I create one variation around this, you will get badly chewed and screwed. All right, so don't take me for granted. How I'll migrate to the next level, you never know. If these things remain weak at your end, trust me, they will always remain weak. So don't assume that, some joker somewhere has given you some inputs and, you're doing fine with all of it. Listen to me carefully. It's in your interest. Okay, and if you think you know it all, get lost. Right? You got my message? Have you got my message? Yes. Maintain modesty in the class. All right? It's going to be right for you and for everyone sitting around you. Maintain that modesty and, try and at least, give me enough reason to teach. So the first space could be filled up in R ways. Now, why? There are R people. From any one of the R people. Any one of the R people could be used to fill up these R spaces. So, I could have filled up this space with P1 or P2 or P3 or PR. R ways. So that means I have used up one person to fill up the space. How many people are left to fill up? R minus 1 people are. That means this could be filled up in R minus 1 ways. That means to create this string, I'll have to fill up all the spaces 1 and 2 and 3 and R, right? Space 3 could be filled up in R minus 2 ways because I've used up 2 people from R. So R minus 2 are left to fill space 3. Space 4, R minus 3. Say the R minus 1th space. Eventually, there are 2 spaces left. And there are 2 people, so, eventually this could be filled up in 2 ways. In 2 ways. Last 2 spaces, that means last 2 people left. So the penultimate space could be filled up in 2 ways. And then you're left with 1 person who would fill up the last space, and that would be 1 way. Right? So that makes it 1 into 2 into 3 up to R. That makes it R factorial. R factorial. Right? So if there are R people to be arranged in order, in R spaces, then that could be done in R factorial ways. So if there are these 3 letters A, B, C, D, and I want to arrange them in all possible ways, 4 letters to be arranged in all possible ways, A, B, C, D, A, B, D, C, A, C, D, B, etc., all of them, then the number of ways in which I could arrange all of them in order is four things in 4 spaces. It would be like 4 factorial ways. That makes it 24 ways. That makes it 24 ways in which I could fill up all these spaces, right? Don't worry. Let me please build up. I mean, I'm trying to drive you to something else. All the conditionality will come in as we grow. But let me just build the foundation in the first place. Okay? There could be umpteen variations around this. I'm not at all worried about the variations. If I've set up the foundation right for you, we'll build up the variations in due course. Just focus on what I'm saying right now, right? So these are spaces to be filled up in r factorial ways by r people, obviously different people. So if there are n different things, 4 different things to be arranged in all possible ways, it's about filling up 4 spaces out of 4 different things, and that can be done in 4 factorial ways. That can be done in 4 factorial ways. Now, can I wipe this off? Yes. Now, if there are 3 things, then they could be arranged in 3 factorial ways if they are all different, right? Now, look, in the previous example that we dealt with, 26 letters, right? Repetition not allowed. 3-letter words that I am constituting. I created 3 spaces, designated them as L1, L2, L3. Designated them as L1, L2, L3. And then I said, fill up the first space in 26 ways, fill up the second space in 25 ways, fill up the third space in 24 ways. That made it 15,600, right? That was creating words, right? That was creating words. So now, what that essentially had was, say for example, I had all possible arrangements of ABC. For example, if these 3 were selected, then all possible ways ABC were arranged. ABC, ACB, BAC, BCA, CAB, CBA, right? These were 6 ways. So it was about, what did it boil down to? It also boiled, you could have looked at it differently. It boiled down to the following. It could have been about selecting 3 letters and arranging them in 6 ways. This is what the whole event was. This 26 into 25 into 24 was what? It was about first selecting 3 letters, any 3 letters from 26 available, and then arranging them in all possible ways, and then arranging them in all possible ways. Yes or no? Which means, suppose, and then we said, well, if the order was important, then the total was 15,600. Then the total was 15,600. And then I said, well, if the order is not important, I will have to suppress the count. I will have to suppress the count. So then, if the order was not important, that means if ABC was the same as BCA, etc., that means order not important. It was only about the selection. If the order was not important, if it was only about the selection, then the total ways in which I could select 3 would be like suppressing this count. These then said 15,600 divided by 6. Now, why this 6? This 6 because, say if I selected any 3 sample elements to create this letter and made all possible arrangements of these, right? Then it was like, for example, a choice of ABC to be arranged in L1, L2, L3. Now every time 3 were selected, then the number of ways in which 3 letters could be arranged in 3 spaces would be 3 factorial. If there were r people in r spaces, then r factorial. So 3 people, call them ABC. 3 spaces, call them L1, L2, L3. The number of ways in which 3 people could be designated to 3 spaces would be 3 factorial. If there were r spaces and r people, then the number of ways would have been r factorial, right? So the reason you have got 6 is because the number of ways in which ABC could be designated to L1, L2, L3 is 3 factorial, which is 6, right? That's why you've got 6 out of it. See, this count turns out to be 6, which is actually 3 factorial. So for every choice of 3 letters, you actually get 6 ways in which they could be ordered in these 3 spaces, L1, L2, L3. Yes or no? Yes, right now? That's why to get the count in which it was, all these were regarded identical. If all these were regarded identical, then the total count would only be 1/6. Because only 1 out of every 3 factorial, only 1 out of every 3 factorial is a relevant count. Isn't it? These are 3 factorial counts, 6 counts, but only 1 is relevant. Therefore, we had to divide by 6 if the order was not important. We had to divide by 3 factorial if the order was not important. That's called suppression of count. Count suppressed to get what is required. If the order is not important, you divide by r factorial. Clear? Now, so far so good, right? Say there were 2-letter words to be created. Suppose there were 2-letter words to be created. L1, L2. Right? 2-letter words to be created, say L1, L2. Then, say L1 could be filled up in 26 ways. L2 could be filled up in 25 ways. 6,500. Right? Now, 6,000, right. Now, what is important is, in this count of 650, the order is important. That means, for example, if A and B were used to constitute filling up spaces L1, L2, then if A and B were used, then AB was different from BA. CD was different from DC, and so on and so forth. Right? So 650 is the number of 2-letter words you could create out of 26 letters, where the order becomes pertinent. But if someone said, no, I only want selection of 2 letters from 26 available. Yes, absolutely, because for every pair AB that I use to create a word, AB or BA, only 1 is relevant. So I have to suppress this count. So every 2 actually means only 1. So I will have to suppress that count. I will have to therefore divide the total count by 2. Therefore, what would be relevant would be 650 by 2. Read it as 2 factorial. Read it as 2 factorial. That would be the number of ways in which 2 could be selected out of 26. Yes or no? Yes, sir. Right. Now, can I wipe this off if you allow me? Suppose I had to create 4-letter words, L1, L2, L3, L4. 4-letter words. Suppose I had to create 4-letter words, L1, L2, L3, L4 out of 26. Again, I am assuming I am not allowing repetition. Okay. Then of course, the first space could be filled up in 26 ways. Second space in? Third space in? Fourth space in? 23 ways, right? These are the number of 4-letter words that could be created. Why words? Because the order is built into it. The moment I fill spaces, I am building order. Yes or no?
Yes, sir.
ABCD will be different from ADCB.
Yes.
Right? Now, so these many sets of words could be created, 4-letter words could be created out of 26 alphabets without repetition. Don't fiddle with your toy. Keep it down. No, the toy is just the calculator. Now, in this, for example, I could have had ABCD being consumed towards constituting this word. ABCD being used towards constituting this word L1, L2, L3, L4, right? So, one way would be ABCD, right? Then you could have had ACDB, BD, you could have had BDCA, and so on and so forth. Suppose I use ABCD. Suppose I use ABCD, right? Then ABCD would give me ABCD, would give me ACBD. It will give me all possible arrangements of these 4 letters in these 4 spaces. That means, when flared up, how many sets will this give me? 4 factorial, right? So every selection of 4 will actually give me 4 factorial. Yes or no?
Yes, sir.
Every time I use 4 letters to create this word, I get 4 factorial words. I get 4 factorial words. Yes or no?
Yes, sir.
That means, if someone told me, just select 4 letters out of 26 available, damn it. Just select 4 letters out of 26 available. I am not goddamn interested in the order. Then, if it's about selecting 4 letters, then out of these 4 factorial, only 1 will be relevant. Out of these 4 factorial, every time you have 4 factorial, only 1 is relevant. If selection has to be made, selection of 4 letters is to be made, then only 1 out of every 4 factorial, right? Out of every 4 factorial counts is important. Right? Only 1 out of every 4 factorial is important. If the order is not important. Right? If the order is important, then this is the count. If the order is important, this is the count. If the order is not important, this count would have to be suppressed. Why? Because in this count, whatever it turns out to be, only 1 by 4 factorial of this count will contribute towards selection. Yes or no?
Yes, sir.
Right? So then if it's a selection, then the total number of ways in which the selection could be made is 26 into 25 into 24 into 23 divided by 4 factorial. This would be the number of ways in which 4 letters could be selected from 26 available. Right now? So I'll tell you, we will mature with these ideas only. With these very simple ideas, we'll mature into reality. Can I wipe this off?
Yes.
So, if this was a count in which order was built in, divide that by 4 factorial, it'll give me a count in which there is only selection, the order is irrelevant. Right? Now, say, same way, if I had 5 letters, L1, L2, L3, L4, L5, now simple, and I had to create 5-letter words out of 26, then it's going to be 26 into 25 into 24 into 23 into 22. These would be the number of 5-letter words. Distinct letters created out of 26 alphabets. But again, in this, let's say if there was a A, B, C, D, E, then in this count, A, B, C, D, E will appear in different orders in how many ways? 5 factorial ways. A, B, C, D, E will appear in different orders in 5 factorial ways. That means if it's only about selecting, then 1 out of every 5 factorial of this will be relevant. Therefore, I will have to suppress the count, divide this by 5 factorial to get the number of ways in which 5 letters could be selected from 26 available, all different. If there were r of these in the string, then I'll have to divide by r factorial, suppress the count and get the selection from the order. Do you understand that? Therefore, I could migrate from order to selection by suppressing the count by perhaps in most cases an r factorial kind of a thing. Do you get me now? Yes, sir. Right, very good. This therefore gives me an opportunity to transit into a result. Okay. Now, till this point, I've said order and I have said selection, but I have not used the conventional terminology towards order and selection. When selection is along with order, if the order is important, then it's a case of permutation. If the order is not important, then it's selection. It's called a combination. That's as simple as this. You know what I'm saying? If the order is important in a given situation, if the order is important in a given situation, it's a case of permutation. If the order irrelevant, it's a case of combinations. Right? Now, with these inputs having penetrated into your intellect, let me give the first formal stint of the subject. Can I wipe this off? Yes, sir. Suppose I have n different things. Suppose I had n different things. Call them T1, T2, T3, Tn. T1, T2, T3, Tn. These are n different things and one instance of each. Which means, you know, T1 can't be used multiple number of times, T2 can't be used multiple. That's when I say there is one instance of each of these things available for use. N different things, T1, T2, T3, Tn, right? And I want to find the permutations of these n things taken r at a time. That means I want to select r things and arrange them in a certain order. That means out of these n things, for example, I would want r of these things to go for a march past. March past, because, you know, don't always think of march past as a march past in brigade ground. It's like I'm talking of an order. That's when I mean symbolically a march past, right? Doesn't necessarily mean a march past. So then, out of n things, I want to create a permutation of r things. That means select r things in order. R things that appear in a certain order, where A, B, C, D would be looked upon as different from A, C, D, B. That's where I say the order is important. So number of permutations of n different things taken r at a time. No repetition. Taken r at a time, no repetition of any one of these things. That means I'm talking of permutations of n different things taken r at a time, no repetition. Now this is a simpler situation because it's about filling up spaces. When I'm trying to build order, I'm filling up spaces, right? So r spaces to be filled up by n different things without repetition. That's the objective, right? So r spaces these are r spaces to be filled up by r things from n available. To be filled up by r things from n available. Moment I fill up these spaces, there is a built-in order. It's a case of a march past then, right? Now, the first space could be filled up by any one of the n things in how many ways? N ways. Any one of the n things without biases could be used to fill up the first space. N ways of filling up the first space. Yes or no? Yes, sir. Now I've used one of these n available. How many left for filling up the second? N minus 1 could be used towards filling up the second space. Then to fill up the third space, n minus 2. To fill up the fourth space, n minus 3. To fill up the fifth space, n minus 4. So to fill up the rth space, n minus r minus 1. See? This is n minus 0. This is n minus 1 less than this. This is n minus 1 less than this. This is n minus 1 less than 4. This would be n minus 1 less than r. Right? Yes, so this would be the number of ways in which these r spaces could be filled up. So this would represent the number of permutations of n different things taken r at a time. Order built into it. Right? And the symbol designated towards this is NPR. Number of permutations of n different things taken r at a time without repetition. If nothing is said, it means without repetition. Right? Is NPR, which is this. Yes or no? Yes, sir. Now, this, as you can see, this is like a n minus r plus 1. Yes or no? This is n minus r plus 1. Right? Now what I do is I multiply it with n minus r factorial. Means the terms after this n minus r factorial would mean what? N minus r into n minus r minus 1 into n minus r minus 2 into n minus r minus 3 up to 1. Yes or no? So look at this entire string. This is like n minus r factorial going as 1 into 2 into 3 into 4 into n minus r factorial. Then n minus r plus 1 into n minus r minus 1 minus 2 n minus r plus 1, then n minus r, then n minus r minus 1, then n minus r minus 2, going up to n. Yes or no? So this whole string now becomes n to 1. So that's n factorial. Yes or no? Naina, not sure about this. I'll explain. Don't worry. Don't worry. Don't worry. See. See. This NPR, number of permutations of n things taken r at a time, n into n minus 1 into n minus 2 into n minus 3 n minus r plus 1 up to this, and then an operation that I performed is I multiplied it with n minus r factorial, numerator and denominator I multiplied with n minus r factorial. But what's n minus r factorial? N minus r factorial is actually n minus r into n minus r minus 1 into n minus r minus 2 going up to 3 to 1. Yes or no?
Yes, sir.
Right now? So that's what. So I'll multiply this numerator with this whole thing, right? So that makes it n minus r into n minus r minus 1 into n minus r minus 2, 3 to 1. The numerator has been therefore multiplied with n minus r factorial. Terms from this point onwards will constitute n minus r factorial. I ought to therefore also divide by n minus r factorial. Yes or no? Yes, now think of it. 1 into 2 into 3 etc. n minus r minus 1, then 1 more than this, then 1 more than this, then 1 more than this. I'm increasing by 1 unit, I'm going all the way to n. So what have I done? From 1, 2, 3, in increments of 1, I have gone all the way to n. What is that? N factorial. Precisely, that's n factorial. That's n factorial by n minus r factorial. That's the number of permutations of n different things taken r at a time without repetition. Got me? Now, order is built into it, obviously. Filling up spaces means there is order, right? Now, look, for example, out of these n things, say, one way in which r could be used to fill up these spaces is like, say, T1, T2, T3, Tr, right? Or different orders of these. So every time a certain set T1, T2, T3, Tr is selected, then a selection in which there is an order built, this would actually give me r factorial ways, isn't it?
Yes, sir.
See, in how many ways can I rearrange these r things? R factorial. R factorial. Yes or no?
Yes, sir.
So in this count NPR, every selection appears in different orders in r factorial ways. Every selection. This is a selection. But how many strings is it producing? R factorial strings is. But if someone says the order is irrelevant, then out of these r factor, every time you have r factorial of these strings, only one is relevant. Out of every r factorial such strings, only one is relevant. One out of every r factorial is relevant when it comes to selection. So if someone says, no, I don't want the order in which the r things appear, I just want to select r things from n available. This n factorial by n minus r factorial is the number of ways in which not only are r things selected, but they are also, every time r things are selected, they are arranged in various orders, right? So this says the order is important. But if someone says, no, I only want to select r things. So let's say this is one mode of selection of r things. Now, in this count, this has appeared r factorial times in different arrangements, in different orders. See, r things arranged in different ways is r factorial. So every unit has appeared r factorial times. This is a family of t's, and in different orders they have appeared in r factorial ways, right? In this count. But only one is relevant when it comes to selection. Out of every r factorial of these, right? This can be broken down into several r factorial units. But out of every r factorial sets of such numbers, sets of such things, only one is relevant. Therefore, if someone says, I want only a selection of r things, then I want to suppress the count, I want to divide by r factorial. This count I want to divide by r factorial, suppress the additional count so that the order gets dissolved. There is no order in it. Then it's only the selection. So if I have the number of selections of n different things, taken r at a time, number of selections of n different things taken r at a time, then suppress the count above by a factor r factorial, right? Divide and conquer, right? So then the required count would be the count that you have obtained NPR in which there is order. Divide that count by r factorial, then the order is removed. Then it's only a selection of r different things out of n different things available without repetition, So this is the number of ways in which r different things could be selected from n different things without repetition. Yes or no? This you realize is n factorial by n minus r factorial by r factorial, and it's referred to as NCR, number of combinations of n things taken r at a time, number of combinations of n things taken r at a time, that is NCR. So if you have n different things and you want to select r different things from this, in how many ways can you do that? NCR ways, where what is NCR? Whatever you have obtained from NPR, you suppress that count by a factor r factorial. Then there is no more order in it, there is only a selection unit that comes by. Are you fine with this or not fine with this? Very good. So number of combinations of n things taken r at a time is this, and do you realize that we only started from first principles, fundamental principles of counting, and moved into this domain, right? No issues with this, right? All of you understand everything that I have communicated so far, right? Now, although I thought this was a little premature introduction to this, I would have rather wanted to introduce a little more before I got into this, but nevertheless, let's get back to ground state. Ground state. All right, again, just because I have taught NPR, NCR, don't develop mental biases and unnecessary affection towards NPR and NCR, right? Still go basic, still stay fundamental, right? Again, for the next few problems, forget that I have communicated NPR and NCR. No one will utter the word NPR and NCR in the class for the rest of this class. Assume I have not yet taught NPR and NCR. Okay? Very good. Let's look at 6. N locks and n corresponding keys are available. L1, L2, L3, Ln. These are the n locks, and obviously their keys, n keys, all mixed up. Kn, these are the n keys, n locks and n keys. Okay. Now every lock has a key that belongs to this set only, but we're not aware of it. So we want to pair the locks and the keys. We want to pair the lock and the keys by trial. All right. Now the question is, what is the maximum number of trials required to pair them up? Assume you are not, huh? All right.
So for one lock there is n pairs. So for n locks there will be n keys. So n into n square.
Look, I know sometimes, you would have solved this problem better when you were in class 6 or 7. Sometimes knowledge pollutes. Okay, I wish I had not started this topic saying that, it's a class on permutation combination. You would have done better. See, okay, now let's, you trucker, despite the fact that you're down with fever, you make more sense than when you are without fever. Okay, so look at lock L1. One of these keys would be relevant for L1. What is the maximum number of trials you require to figure out, do you require n minus 1? Yeah, if you have tried n, then the last n minus 1, then the last one ought to be the key of L1, isn't it? Do you want to try every key and see? No, yeah, if you have tried n minus 1 keys and they have failed, then you don't have to try the nth key. That ought to be the key for this, isn't it? So the maximum number of trials for n1, first you will do n1 only, right? L1 only, n minus 1 trials, right? Now, n minus 1 locks remain and n minus 2 keys remain. How many trials required for L2? n minus 2 or 1 or how much? N minus, see, okay. If there are P locks and P keys, how many trials are required for the first lock? P minus 1. Now there are n minus 1 locks and n minus 1 keys. How many trials will you require? N minus 2, isn't it?
Yes, sir.
See, if there were n locks and n keys, then for the first lock, you required one trial less than the number of locks and keys. So forget L1 and forget K1. Now there are n minus 1 locks and n minus 1 keys. Then for the first lock, the maximum number of trials you require to figure out the key for this lock would be 1 less than the total number of locks. You arrived at the formula already, right? So n minus 2 ways of figuring out the key for L2. Yes or no? Yes. How many trials you require for L3? N minus 3. Because now you forget all about L1, L2 here. There are n minus 2 locks, n minus 2 keys. The number of trials required for this lock would be 1 less than the total number of locks. That is n minus 3 trials. Zero, isn't it? I mean, at the end, you're left with 1 lock and 1 key. Do you still need a goddamn trial for that lock and key? You don't, nah? So, going this way, 0 trials required for Ln, because the last lock is left with the last key, and that ought to be the key for that lock. You don't need a trial. You might unnecessarily want to poke the key into the lock. That's your choice. If you're uselessly sitting, you could do that. Okay. Now, think of it, the total number of trials. Yes, adding, absolutely adding here. You have performed these many trials here. For every trial, I give you a mango. So number of mangoes will be equal to number of trials. That way you will understand better. Then you have got n minus 2 more mangoes. That would be some more trials. And then you've got n minus 3 mangoes. And then you've got 0 mango. How many mangoes have you got in all? Multiply or add? Add now. Very simple. You want to add these numbers, dude. 1 plus 0. Before 0, there ought to be a 1, because if you are going in this direction, it's increasing by 1 unit. This is the total number of trials. Total number of mangoes kitna mila? This much, and then this much, and then this much. Right? You won't want to multiply. You want to add. Right? Huh? Right, so no trial required. Right. So this would be the maximum number of trials. Sum of the first n minus 1 natural numbers, isn't it? It's sum of the first n minus 1 natural numbers. 1 plus 2 plus 3, etc. going all the way to n minus 1. Sum of the first n minus 1 natural numbers is, see, starting from here, n minus 1 into n by 2. You came close. I don't know where you goofed up, but you came close, Prakhar. This would be the maximum number of trials, right? All right. Again, no NPR, NCR taught, so don't use that. Now, how many 3-digit numbers? We want 3-digit numbers D1, D2, D3. 3-digit numbers from this set 1, 2, 3, 7 and 9. We want 3-digit numbers to be created. Repetition allowed. That means I have large number of 1s available, large number of 2s available, large number of 3s available, 7s, 9s. I can use them in any number of ways I want to, right? So the first, so these are 3 spaces which will designate the 3 digits, right? So the, and to create a number, the order will be important. So it's okay to fill spaces when it comes to counting the number of numbers, right? Because the order in which the digits appear will be relevant. So then the first space designated as D1 could be filled up in 5 ways. I'm talking of the cases where repetition is allowed. So 5 ways of filling up D1 leaves me with no less ways of filling up D2, because if I have used 1 for D1, then I could reuse it for D2. So 5 ways of filling up D2, 5 ways of filling up D3, that makes it 125 ways. 125 3-digit numbers in which repetition is allowed, right? No repetition. That means D1, D2, D3 ought to be distinct. There is only 1 copy of each of these available. So the first space, D1 could be filled up in 5 ways, leaving me with 1 digit less for D2. So D2 could be filled up in 4 ways, D3 in 3 ways, 60 ways. Repetition not allowed would give me 60 ways of creating 3-digit numbers in which digits don't repeat. Are you all there with me? You got me now? Pakka? All of you? Then, no, if we had 0, then this would be prohibited. Suppose I had 0, 1, 2, 3, 7, 9, suppose. Okay. Then, of course, this can be filled up in 5 ways only, because 0 will not be allowed. If it's a proper 3-digit number, then 0 will be prohibited from filling up the space. So this could be filled up in only 5 ways, and this could be filled up in 6 ways, and this could be filled up in 6 ways, because 0 could appear in the units and the tens place, right? So 36 into 5, 180, right? And in this, if there is no repetition, then again in the first place I can't fill up the first space in 5 ways. In 6 ways I can fill it up in only 5 ways. Okay. So out of 6 I have used 5. I'll be left with, I've used 1, I'll be left with 5 ways of filling up the space, and then 4 ways of filling up the space. Right. Got me? Very good. Now let's look at the next one. See, I certainly, this is a little bit of a sensitive topic in which, you know, it's counting and it's very basic. Therefore, you know, it's important that, you know, we don't suddenly jump to a level where we ignore the foundation. It was important for me to, you know, go through some things that actually look so stupid ab initio, but then those are the things where you would goof up, you'll realize that. So I'm spending so much energy doing all this because I know these exactly would be the areas where, you know, you would falter. Right. If 3 dice, D1, D2, D3, these are 3 dice and they are rolled. Find the number of ways of getting the same number on all of them. Obviously, there are only 6 ways. You don't have to learn anything to answer this. I mean, all could be 1. Same number means all D1, D2, D3 would give me an output 1, or all would give me an output 2, all would give me an output 3, or 4, or 6. So this count obviously is 6. To get the same number on all 3 is 6 ways, right? To get a different number on all the 3 dice, to get a different number on all 3, so D1 could be any 6 then. D1, the dice D1 could be any one of the 6 numbers 1 to 6, but D2 would be only 5, because the one that has appeared in D1 is prohibited from appearing for D2. So D2 would be only 5 ways and D3 would only be 4 ways. So this way you will have all the 3 dice giving you different numbers, right? Nine. In problem 9, we have 5 different books: B1, B2, B3, B4, B5. These are 5 different books. These are 5 different books and there are 3 students. Yeah, this is what happens nowadays. There are fewer students and more books. In how many ways can we distribute these 5 different books to 3 different students? You're not going to dump a student onto a book. You will take a book and allocate it to a student, isn't it? Not the other way around. So this is logical, understand this. Right? So you take book B1 and examine who all it could go to. It could go to any one of the 3 students. Right? It could go to any one of the 3 students. So event 1 related to allocating book B1. Right? So book B1 could be given out in 3 ways. It could be given to any one of the 3 students. Yes or no? Yes. Now there is no rule which says that if student S1 has received a book, he is not eligible to receive more books. You know what I'm saying? In the given problem, which has no such condition, it doesn't say that every student must necessarily have a book. It doesn't say that a student must have 2 books or 3 books. It says if a student has received a book, he is not necessarily deprived from receiving more books. Right? You know what I'm saying? What are the various events in this problem when I'm allocating books to students? Event 1, allocating book B1, and it's not or. You don't have an option of not allocating B1. Event 1, allocating B1 to these students, any of the 3 students. Event 2, allocating book B2 to any of the 3 students. Event 3, allocating B3 to any one of the 3 students. These are the various events. So event 1 and event 2 and event 3, event 4 and event 5. So it's going to be a case of multiplication. So book B1 allocated in 3 ways and book B2 allocated in 3 ways and book B3 allocated in 3 ways, B4 allocated in 3 ways, B5 allocated in 3 ways. That makes it 3 to power 5. That makes it 243. Right? So 243 ways in which the 5 books could be given to 3 students. Yeah, absolutely. I'm saying in your endeavor to allocate books to students, you would look at 5 events. Event 1, allocating book B1, and then event 2, allocating book B2, and then event 3 allocating book B3, event 4 allocating book B4, event 5 allocating book B5, and it's event 1 and event 2 and event 3 and event 4 and event 5. Event 1 allocating B1 could take place in 3 ways, and event 2 which is allocating B2 3 ways, and event 3 3 ways, 3 ways, 3 ways. Multiply all the events, that makes it 3 to the power 5, 243 ways in which the books could be allocated to students. Yes or no? Clear? Let's look at the next one. So far so good, right? All right, problem 10. A student appears for an objective test comprising 10 MCQs. Okay. So, problem 1, and it's given that each question, there are 10 questions, each with 4 choices, as is traditional. So, choice A, B, C, D, etc. Question 2, A, B, C, D. Going this way, question 10, A, B, C, D. Right? There are 10 questions, each question has 4 choices. So 10 MCQs in all. Now in the first part of the problem, they say for every question, that means in the first part, for every question, only one option correct. That means question 1 would either have A or B or C or D. For question 2, A or B or C or D, etc. Right? Now, how many different sets of answers can a student give? Yes, it's about 10 events. An answer set means answer to question 1 and answer to question 2 and answer to question 3 and answer to question 10, right? 4 events, 10 events, 10 events. Event 1 answering question 1, event 2 answering question 2. In order to create answer sets, first event would be about answering question 1. How many answers can he give to question 1? 4 ways in which question 1 could be answered. A or B or C or D. Or means add. Right. So question 1 could be answered in 4 ways. That's event 1. Creating an answer set is deploying event 1 and event 2 and event 3 and event 10. Creating an answer set would be, a complete answer set would be deploying these events. Event 1 answering question 1 and event 2 answering question 2 and event 3 answering question 3 and event 10 answering question 10. Event 1 can take place in 4 ways, because event 1 could result in any one of the 4 answers coming up, A or B or C or D. Event 2 is answering question 2, which will create 4 answers, A or B or C or D. So 4 ways of answering question 2, 4 ways of answering question 3, 4 ways of answering question 10. So then the number of ways in which 1 and 2, we'll assume that all questions are answered. Right? No negative marks, so he's answering all questions. Okay, so the whole range comprises taking care of event 1, that is answering question 1, and event 2, that is answering question 2, and event 10, that is answering question 10. In how many ways can that happen? Event 1 in 4 ways, and event 2 in 4 ways, and event 3 in 4 ways, event 3 in 4 ways, event 4 in 4 ways, event 10 in 4 ways. So that makes it 4 to power 10 sets of ways in which event 1, event 2, event 3, event 10 could all come up. That makes it 4 to power 10 different answers. Every event comprising event 1 to event 10. Event 1 to event 10 is an event that leads to one answer set. So 4 to power 10 ways of deploying event 1, event 2, event 3, event 10 would give me 4 to power 10 different sets of answers. 4 to power 10 different sets of answers, yes or no?
Yes, sir.
Right? The next part of the problem is more than one option can be correct. All right, more than one correct option. So this was for every question. More than one correct option. Okay, more than one correct option. So let's see in how many ways one particular question could be answered. If more than one answer, more than one option is right, if more than one option is right, let's examine the number of ways in which a certain question could be answered. For example, question 1, which is A, B, C, D. Let's see how many sets of answers could be produced for question 1 if multiple options could be correct. Right? Okay. Now, look, we'll assume again that he's certainly answering the question. Right? We'll assume that he's certainly answering the question. Now, question 1, he'll look at option A and he'll say, heads, I'll mark A, tails, I will not mark A. So, in how many ways can he deal with A? Two ways he can deal with A. Either mark A or not mark A in his answer scheme. In his answer scheme, for let's say a certain question, he may look upon A favorably or unfavorably. So, he can deal with A in two ways, either mark A or not mark A. Yes or no? So, the number of ways in which he can deal with A is 2. Same thing when he comes to B. Heads, I'll take A, B, I'll not take A. So, the number of ways he can deal with B is favorably or unfavorably. Either he takes B into the pocket or he doesn't take B into the pocket. So, 2 ways of dealing with B, and it's not like A or B, it's A and then B. 2 ways of dealing with A and 2 ways of dealing with B and 2 ways of dealing with C. He can either choose C as an option or not choose C as an option. Yes or no? 2 ways of dealing with C and 2 ways of dealing with D. So, in all, 16 ways in which he could answer. But, no.
None of them.
Yes, there will be one possible answer in which, see, in this 2, there is one in which A is not there. There is 2 ways he dealt with B, out of which there is one case in which there is no B. 2 ways he is dealt with C. Therefore, out of the 2 ways, there is one case in which C has not been included. There is one case in which D has not been included. That means, in this count of 16, there is one case in which A, B, C, D, none of them have been included. Yes or no? So, actually, if he is forced, so he is not allowed to give such an answer in which he gives nothing. He's forced to commit to an answer. We'll assume that. So, if he is forced to commit to an answer, he'll say, well, 16 ways in all for a given question, in which, out of which there is one case in which A, B, C, D, none is included. So, I'll have to exclude that case, because that option is not allowed, in which he neither marks A, nor B, nor C, nor D. That's excluded from this. So, from the 16, I exclude 1. So, that makes it 15. So, how many sets of answers are possible for 1? 15 sets of answers are possible for 1. Yes or no? Yes, 15 sets of answers for 1, 15 sets of answers for 2, 15 sets of answers for 10. So, in all, how many sets of answers? 15 into 15 into 15, 10 times 15 to power 10. 15 to power 10.
the number of ways of choosing 4 options plus the number of ways of choosing 3 options plus the number of ways of choosing 2 options plus the number of ways of choosing 1 option.
Agreed. Where do you live? You go via Park Street? But you could have. You're right. But we want to be simpler than that, isn't it? So I accept what you're saying, but this would be simpler. Absolutely from scratch we do it, right? But I don't disagree with what you're saying. Okay? So that's 15 to power 10. Clear? Let's look at the next one. A set has n elements. Say A1, A2, A3, AN. N elements in a set. A set has n elements. Let's say this is a certain set, call it A. And we want to create subsets out of this. We want to create subsets out of this. Question is, how many subsets? For example, A1 is a subset, A2 is a subset, A3 is a subset, AN is a subset, A1, A2 is a subset, A2, A3 is a subset, A4, A5 is a subset, A1, A2, A3 is a subset, AN minus 1, AN minus 2 is a subset, and so on and so forth. Or no element is also a subset, that's a null set. Right? If I don't choose anything, that's also a subset, that's called a null set. A null set is also a subset. Huh? This itself is a subset. This itself is a subset. All elements is a subset. No element is a subset. Some elements is also a subset. Right? Let's be clear about this understanding. Right? Now, to create a subset. To create a subset. These are two braces in which I am creating a subset. Creating a subset involves the following events. To create a subset, the following events are involved. Event 1. Whether I am going to include A1 in this subset or not include A1 in this subset. Isn't it? Event 2. Whether I am going to include A2 in this subset or not include A2 in this subset. To create a subset, these are the involved events, right? Whether I am going to include A3 in this subset or not include A3 in this subset. Whether I am going to include A4 or not include A4 in the subset. These are the various events involved towards creation of the subset. Yes or no? Yes, sir. Okay. So, event 1. Whether or not to include A1 is actually two possibilities. A1 could be dealt with in two ways. Either included in the subset or not included in the subset. Two ways of dealing with A1. Yes or no? Yes, sir. Two ways of dealing with A1. So A1 may or may not be in the subset. Again, inclusion or exclusion of A2 does not depend on what I have done with A1. Right? So as far as A2 is concerned, how many ways of dealing with A2? Two ways of dealing with A2. So that's event 2. But it's A1 and A2 because I must in principle decide what I have to do with A2. So it's not like, I can exclude A2 from my decision making, right? So dealing with A1 in two ways, dealing with A2 in two ways, either include A2 or not include A2. A3, two ways of dealing with A3, either include it in the subset or not include it in the subset. How many ways of dealing with AN? Two ways of dealing with AN. So the entire set of events that are involved towards creation of the subset, the entire set of events that are involved towards creation of the subset is event 1 into event 2 into event 3 into event 4 into event n. Event 1, two ways. Event 2, two ways. Event 3, 2 ways. Event 10, 2 ways. So that makes it 2 power n. And this includes a case in which A1, A2, A3, An all are included. That's one subset included in this. Also includes a case, the second possibility, A1 not included, A2 not included, A3 not included, An not included. None included, that will create a null set. So this, huh? Yes, because see, in my attempt to select A1, I have included two possibilities, one in which A1 selected, one in which A1 not selected. A2 selected, not selected. So this 2 to the power includes a case in which A1, A2, A3, An, none is selected or all is selected. So it includes two cases, one in which all are selected, one in which none is selected. None selected would be the null set. Right? So 2 to the power n subsets. 2 to the power n subsets. We call a natural number odd looking if all its digits are odd. If all its digits are odd, that means what are the odd digits possible? 1, 3, 5, 7, 9. These are all digits. And we are trying to create odd looking numbers, all odd looking numbers, natural numbers. 4-digit odd looking numbers. 4-digit odd looking numbers. 4-digit odd looking numbers means A, B, C, D, in which A, B, C, D must all be odd numbers. Odd looking natural numbers would be those in which all digits are odd. All digits are odd. Now, absolutely. So then, in how many ways can I deal with A? 5 ways. Yes, see, again you don't have to say, because 1, 1, 1, 1 is an odd digit, odd looking number, isn't it? So obviously it has to be included. 2, 2, 2, 3, 3, 3, 3 is an odd looking number, or 1, 1, 3, 3 is an odd looking number. So obviously in this repetition is allowed. If you have to find all, then repetition is allowed. Right? So 5 ways in which A could be selected. Any one of the 5 natural numbers could be used to fill up the space. Any one of the 5 natural numbers could be used to fill up the space. Any 5, that makes it 625 4-digit odd looking numbers. 625 4-digit odd looking numbers. Okay. Now, we have a word equations. Equations, right? How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 letters. And we want to create all 9-letter words out of these. It's like just rearranging these in different ways. 9 factorial, if you have 9 different digits, 9 different entities, 9 different things. These are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different things, isn't it? These are 9 different things. To be arranged in 9 spaces. To be arranged in 9 spaces. 9 different things to be arranged in 9 spaces. In how many ways can I? 9 factorial ways. Are different things to be arranged in R spaces can take place in R factorial ways, right? So 9 factorial different ways in which these are called 9 factorial permutations of these. This is 9 factorial permutations of this word. 9 factorial permutations of this word. We call it 9 different permutations of this word. Now, listen to me again. Can I wipe this off? Yes. Huh? 9 different things. See, what we are trying to do is we are trying to arrange the letters of the word equations in all possible orders, right? So it's like 9 different things, 1, 2, 3, 4, 5, 6, 7, 8, 9, to be arranged in 9 spaces. In how many ways can we do that? 9 factorial. So we say 9 factorial permutations. We say 9 factorial permutations of these 9 different things. 9 factorial permutations of these 9 different things. That's what we say. Got me? Permutations means order in which they have to be arranged. Okay. Now, look. Suppose I have a word called Ohio. All right. Now, how many letters are there? 1, 2, 3, 4. 4 letters. But they are not all different. In which, out of these 4 letters that constituted this word, there are 2 that are alike and of one kind, and others all different. This is a 4-letter word. This is a 4-letter word. Sorry, huh? Out of which 2 are alike and of the same kind. OO. Clear? I want to create permutations of these. When I say create permutations, means create all possible arrangements. Create all possible arrangements. Now, if they were all different, then it would have been 4 factorial. Ways in which I could have arranged these 4 letters. They would have been 4 factorial permutations if they were all different. I mean, if I said LUCK, these are 4 different, and I would have had 4 factorial permutations of this. ULCK, etc. I could have created 4 factorial, including this, I could have created 4 factorial arrangements of these, right? Because they were all different. In this case, they are not different. They are not different. There are 2 O's that are alike. So what would happen is, what we do here is, for a moment, your attention please, for a moment, imagine these O's to be different. Mentally conceive these O's to be different for a moment. All right, I want to find the number of permutations of these, total number of rearrangements, despite 2 O's being the same, right? But what I do is, I have knowledge of the case in which, well, they were all different, then it would have been 4 factorial. But here we have a different situation. There are 2 letters that are alike. There are 2 letters that are alike. For a while, let me assume that they are different. Let me call one O as O1, the other O as O2. Let me call one O as O1, the other O as O2. So essentially I am distinguishing between the 2 O's, only for the heck of it, so that I can reduce the problem to a known problem. I am choosing to call the 2 O's different so that I could reduce this problem to a known problem. That's the tenet of mathematics. That's what we try and do. Always try and reduce a situation to a known situation, a situation with which we have bred familiarity, right? So let me imagine the 2 O's to be different, call them O1 and O2, right? Now, if the 2 O's are different, if I chose to call them O1 and O2, then the number of ways in which, number of arrangements of the letters that I could create would be how many? 4 factorial. I could have created 4 factorial permutations of these. 4 factorial permutations could be created. That means, for example, I could have created a O2, H, I, O1. I could have created, say, O1, O2, HI, O2, O1, HI. Yes or no? Yes, sir. Yes or no? And 4 factorial permutations means 24 on the pretext that O1 and O2 are different. Hey, but come back to this. Are these the same or different? This is my scheme of permutations. These are the various arrangements. In this arrangement, look at these two, for example. Are they actually the same or different? They are actually the same. The moment I remove these subscripts, they are the same. They are actually meant to be the same, right? That means only one of them should have been counted in this. If I look upon them as different, there would be 24 such cases. 1 case, 2 case, 3, 4, 5, etc. Right? But now, think of O1 and O2 to be the same. Right? If you think of O1 and O2 to be the same, then this is the same as this. So only one out of these two is relevant. Yes or no? Yes, sir. Are these the same or different? Actually, they are actually the same. But in this 24 count, they are looked upon as different. But only 1 out of 2 should have been counted. Only 1 out of 2 should have been counted. Right? Similarly, I could have had, say, HI O1 O2, HI O2 O1. In this 24, this permutation is included. These two appear different, but are they actually the same or different? Same. So only half of these, half of this, half of this will be included. The actual count would only be half of 24. Why? Because for every 2, for example, there is only one which is relevant. For every 2, there is only one count which is relevant. For every 2, there is only one count which is relevant. Why? Because O1, O2 are indistinguishable. They are the same. So then the actual count should have been 24 divided by 2. Right? So there were 4 things. In this, there were 4 things in which 2 were alike. There were 4 things in which 2 were alike and of the same kind, obviously. That means then the number of permutations of these 4 things in which 2 were alike turned out to be 4 factorial divided by 2 factorial. Taken all at a time. Number of permutations, what we got is number of permutations of 4 things, not all different. Number of permutations of 4 things, not all different. 2 are alike and the rest different. 2 are alike and the rest different. Turned out to be 4 factorial by 2. If there were 4 different things, it would have been 4 factorial permutations of 4 things taken all at a time. 4 different things taken all at a time would have been 4 factorial. But 4 things in which 2 were alike, reduce the count by 2 factorial. Reduce the count by 2 factorial when all were taken. Similarly, suppose, let me change this a little bit. But are you all in sync with me? Huh? Right now? Now, suppose instead of Ohio, let's say there was a city called Ohio. Five letters. I want to take all of them in creating permutations. In creating rearrangements, I want to take all 5. If they were all different, then it would have been 5 factorial. But now, I have 3 of them out of 5, 3 are alike and of one kind. Yes or no? So what I do is, well, for a moment, I imagine these to be different. For a moment, I imagine these to be different, O1, O2, O3. If they were actually different, then the total number of permutations would have been 5 factorial taken all at a time. Right? Say, for example, there was O1, O2, O3, HI. Suppose there were O1, O2, O3, HI. Clear? There would also be then O1, O3, O2, HI. There would also be O2, O3, O1, HI. They would also be O2, O1, O1, O3, HI. They would also be O3, O1, O2, HI. They would also be O3, O2, O1, HI. Yes or no? Yes, sir. This for example, right? Hey, that means in this 5 factorial, all these 6 are actually 3 factorial. Do you see that? Because it's like I have arranged O1, O2, O3 in all possible ways. That gives me 3 factorial. That's why I've got 6 of these. I've got 3 factorial of these. That means out of these 3 factorial, do you really think they are all different? They are the same. Why? Because dissolve the subscript, they will look the same. The subscripts were only fictitious, created by us, pseudo, right? So out of these 3 factorial, only 1 is relevant, right? Out of these 3, so out of every 3 such factorials, only 1 is relevant. So out of these, there are a total 5 factorial. The total count must get suppressed by a factor 3 factorial. Yes or no? Yes, the total count gets suppressed by a factor 3 factorial. Right? So, if there were 5 things in which 3 are alike and of one kind and the rest different, then the number of permutations of 5 things taken all at a time would not be 5 factorial, but would be 5 factorial divided by 3 factorial, because 3 are alike and of one kind. Yes or no? Yes, sir. Therefore, a generalization of this is what we were seeking. If there are n things, not all different. If there are n things, not all different. There are, out of these n things, alpha of these things are alike and of the same kind, then the number of permutations, that means number of arrangements. When I say permutations, now I mean number of arrangements of these n things taken all at a time, in which, okay, in which I have already said, taken all at a time, in which alpha are alike, right, and the rest different, and the rest alpha are, out of these n things, alpha are alike, and the remaining n minus alpha things are all different. Then the number of permutations of these n things taken all at a time, that means taken all n at a time, is going to be given by n factorial by alpha factorial. The way you can look at it is, think of these alpha things as different, call them A1, A2, A3, A alpha, then you would have got n factorial. Suppress that count by alpha factorial. Suppress that count by alpha factorial so as to remove duplicity of count. Same way like we illustrated, right? And so if we had, in a more general sense, if there were n things, in which alpha were alike of one kind, beta things were alike and of a second kind, and say gamma things were alike and of a third kind, and the rest different, then the number of permutations of these n things in which alpha are alike and of one kind, beta are alike and of a second kind, gamma are alike and of a third kind, and the rest different, would be given by That means each of these will suppress by 1 by this factorial. This will suppress by beta factorial. This will suppress by gamma factorial. Total count will then turn out to be n factorial by alpha factorial into beta factorial into gamma factorial. Number of permutations of n things in which alpha alike and of one kind, beta alike and of a second kind, gamma alike and of a third kind will be this. Got me? Let's get to ground state then. Yes, all of them have to be suppressed. Yes. So far, so good, right? All right. How many triangles can be formed by joining the vertices of a hexagon? Number 14. How many triangles? We want to find the number of triangles. Hello? From the vertices of a hexagon. Right. See, suppose the vertices of the hexagon were A1, A2, A6. I mean, I'm only writing them like this. They will not appear this way, right? The hexagon would be this way, etc. Right? I'm just writing for convenience. These are the 6 vertices of a hexagon. Don't use NPR, NCR, etc. Nothing. I have not taught NPR, NCR to you. Okay? So, now, how many triangles could be formed out of the vertices of a hexagon, say? So to create a triangle, what would you need? 3 vertices would be required, right? 3 vertices would be required at a time, right? So let's say I have 3 spaces. Suppose I have 3 spaces in which I am going to designate the vertices that I have chosen for the triangle. You know what I am saying? Yes, sir. I have 3 spaces which I will fill up to get the vertices of the triangle. So it's like to create a triangle, it's like in how many ways the 3 vertices could be selected. In principle, isn't it? In how many ways the 3 vertices could be selected will give me the number of triangles. What we do is, I create 3 spaces, and in these 3 spaces, I am going to delegate the vertices that I am going to choose for the triangle. Right? Are you lost or are you there with me? There? Okay. So in the first space could be used up by any one of the 6 vertices, right? Could be used up by any one of the 6 vertices. 6 ways. Yes or no? Yes, A1 or A2 or A3 or A4 or A5 or A6, yes, right? The second space, 5 ways. Third space, 4 ways. Now, no, I'm not done. You might be tempted to think that, well, the number of triangles would be these. Now, yes, the point is, say, in this, the order of selection of the vertices has come in the sense, you know, in this 120, which I have obtained out of filling up spaces, therefore I have built order in it. I built order in it. In these 120, in this count of 120, suppose a vertex A1, A2, A3 is there. right? If this is a triangle, that means in this 120, if A1, A2, A3 have been obtained, then A1, A3, A2 has also been obtained. Then A2, A3, A1 has also been obtained. A2, A1, A3 has also been obtained. A3, A1, A2 has also been obtained. A3, A2, A1 has also been obtained. Yes or no? But do they represent different triangles? They represent the same triangles. They represent the same triangle. That means in this 120, every 6 of these actually represent one triangle. Every 6 of these represent only one triangle. Therefore, 6 is like 3 factorial. See, 1, 2, 3. So that's why you've got 3 factorial. So out of these 120, every 6 actually represents one physical triangle. That means every 3 factorial will represent one triangle. Therefore, the total count will not be 120 but will be 120 divided by 3 factorial. So the number of triangles will be 120 divided by 3 factorial to suppress duplicate counts. To suppress duplicate counts. Right? 3 factorial, which is 6. So 20 such triangles. 20 triangles could be created. Right? See, creating a triangle means what? Choosing 3 vertices. Right? So what I do is, I take 3 spaces and fill the 3 spaces with the vertices I want to select. Right? So the first space I fill up in 6 ways, second space in 5 ways, third space in 4 ways. Right? 120 ways. But in this 120, what I have done is, I built an order. See, is a triangle A1, A2, A3 different from a triangle A3, A2, A1? They are the same. But in this count of 120, if a triangle A1, A2, A3 has been selected, then a triangle A1, A3, A2 is also selected. A2, A3, A1 has been selected. A2, A1, etc. All of these. That means instead of one triangle, this actually represents one triangle, but 3 factorial triangles have appeared. That means every 3 factorial of these counts of 120 represents only one triangle. Therefore, I will have to get the real number, actual number of triangles, I will have to suppress the count by 3 factorial. That's why I divide by 3 factorial to get 120 by 3 factorial to suppress the count, additional count. 40 such triangles, right? 20 such triangles. Let's look at the next. Right, you are sitting, I'm standing. You are not in pain, I'm in pain. And you are so many more years, decades younger. Okay, so, you know, you can listen to me. How many diagonals are there in a polygon of n sides? Clear? Okay, A1, A2, A3, AN. A polygon of n sides is what we have. Polygon of n sides. That means n vertices. That means n vertices, A1, A2, A3, AN, and I want to create a diagonal. I want to create a diagonal. Now, a diagonal would mean join of 2 non-consecutive vertices. A diagonal would mean join of 2 non-consecutive vertices, because the join of 2 consecutive vertices will give me a side. Right. Now, look, let's forget that the join of 2 consecutive vertices is a side. Let me look upon that also as a diagonal. For a moment, let me say, for a moment, I'll remove that additional count later on, but for a moment, let me assume that if I join any 2 vertices, I get a diagonal. From that, I'll remove the number of sides. There are n sides, I know. Right? For a while, assume that the join of any two vertices is a diagonal. So let's figure out the number of ways in which two vertices could be joined. That will give me the number of so-called diagonals. Let me find out the number of ways in which two vertices could be joined. Let's say if I select any vertex, say AI, AJ are two vertices that are joined. Creating a diagonal tentatively would mean join of two vertices, AI and AJ. Now, AI could be selected in n ways. The first vertex could be selected in n ways. The second vertex then could be selected in n minus 1 ways. Because if AI is selected, then the second vertex cannot be AI. It would be any one of the remaining n minus 1 vertices. Yes or no? Yes, sir. Right? Now, the problem here is that if in this count, in which actually I have filled up spaces, first vertex, the space for first vertex filled up in n ways, space for second vertex filled up in n minus 1 ways. The order has been built in. That means if in this count, which is n into n minus 1, if A1 and A2 have appeared, then A2, A1 will also appear. That means there is duplication of count here, there is a double count here, right? So from this n into n minus 1, I will divide by 2 to get the number of ways in which two vertices could be joined. This will give me the number of ways in which two vertices could be joined. Yes or no? This gives me the total number of ways in which two vertices could be joined. But not all are diagonals. From this, I want to remove n, the sides. From this, I want to remove the number of sides n. Yes, yes. See, first thing that I am addressing is, in how many ways can you join two vertices? Any two vertices. So I take two spaces. The first space that represents the first vertex, the second space that represents the second vertex. The first vertex can be filled up in n ways. The second vertex then is left with n minus 1 choices. So A1, the first and the second spaces could be filled up in n into n minus 1 ways. Right? This then falsely seems like the number of ways in which two vertices could be joined. No. What it actually represents is the join of A1, A2. It also represents A2, A1. It represents A3, A4. It also represents A4, A3. Right? So this n into n minus 1 does not represent the number of ways in which two vertices could be joined, but represents twice that many. Isn't it? So you want to divide by 2 to get because you don't want to look upon A1, A2 and A2, A1 as different joins. They are the same. Yes. First vertex could be selected in n ways. Right? The first vertex could be selected in n ways. I hope I am not crossing your dielectric breakdown limit. Right? No, you learn about dielectrics in class 12, don't worry. So this n into n minus 1 represents, for example, A1, A2 as well as A2, A1, but only one is relevant. So I divide by 2 to get the required count. N into n minus 1 by 2 is the number of ways in which any two vertices could be joined. But this also includes the n sides. It also includes A1, A2, A2, A3, A3, A4, because join of any two vertices is what I have got by n into n minus 1 by 2. And this includes n sides, but the n sides are not diagonals. So I remove n from this count, then I get the diagonals. N into n minus 1 by 2 minus n will give me the number of diagonals.
So like we choose one point, and for the second point we have left the two.
Right. Absolutely. N minus 1. You can add all of them then. Perfect. No issues. Sounds okay? Yes. A man has 5 friends. Nowadays, No one has 5 friends given Facebook. You know, you have that many friends. When we were students, we actually had 5 friends and actually had 5 friends. Now you have thousands, but none. Yes. Five friends means obviously 5 different friends. F1, F2, F3, F4, F5 are the 5 friends. In how many ways can he invite one or more to a party? Yes, it's about when in his invitation list, he does the count friend by friend. One friend, how many ways can he deal with a friend? Either invite him or dump him. Right? So with F1, number of ways in which he can deal with F1 is 2. And number of ways in which he can deal with F2, either invite or not invite F2. 2, 2, 2. That makes it 2 to the power 5, 32. Yes, because this, yes, all of you are right. This includes that one case in which he is invited no friend, kisko party dega? Right? So exclude that one case in which he invites no one. So that makes it 31. 31 ways in which he could invite one or more friends to a party. Okay, very quickly. 17. Now we have hello, A, B, C, D. Hello. You know, don't get impatient. Some more time. I'll let you go. Find the number of ways in which one or more letters can be selected from this. We want to find the number of ways in which one or more letters could be selected from this set. Right? For example, you know, I could select A, or I could select ABC, or I could select AA, BD. Find the number of ways in which one or more letters could be selected from this set. Now, see, that's given. See, in my mode of selection, can I have your attention please? In the mode of selection, there are 4 A's available. These are identical entities, isn't it?
Yes, sir.
While I'm making a count, then when I'm making a selection, right? A selection would be the number of ways in which I could deal with these A's, and the number of ways in which I could deal with these B's, and then the number of ways in which I could deal with C, and then D, and then E. That will give me the total count. The total count would be what? The number of ways in which I would deal with A's, number of ways in which I would deal with B's, and C, and then D, and then E. The total number of ways in which I can deal with them together, compounded, that will give me the required count. That will give me the required count in which one or more letters could be selected. Number of ways in which one or more letters could be selected. How many A's are there? 4 A's. In how many ways can I deal with them? Damn it, 5 ways I can deal with them. Because in a count, when I'm creating a set, I'm saying there are 4 A's, 3 B's, a C, a D, and a E. I want to select one or more letters from these. Don't think about permutation combination. Okay? Just think of a simple count. I want to select one or more letters from these. Now, the number of ways in which I can select one or more letters, when I'm making that selection, what am I doing? One, I come down to these A's. Find the number of ways in which I could deal with these A's in my attempt to create that selection. And then I come to these B's, find the number of ways in which I could deal with these B's in that selection. Find the number of ways in which I could deal with these, the C, the D and the E to create that selection. Yes or no? Is that not the problem? Right? Now, how many A's are there?
4.
In my selection scheme, in the string that I am selecting, that comprises A's, B's, C's, D's, E's, etc. In my string that I am selecting, the number of ways in which I could deal with 4 A's. They are all identical, by the way. Either I select 1 A, or I select 2 A's, or I select 3 A's in that scheme, or I select 4 A's, or none. How many ways I can deal with A's? 5 ways I can deal with A's. Yes or no? Select 1 A, or 2 A's, or 3 A's, or 4 A's, or no A. Right, absolutely. So 5 ways I can deal with A's. Yes or no? Yeah? Now, there are 3 B's. In how many ways can I deal with B's? 4 ways. Either select 1 B, or 2 B's, or 3 B's, or no B, 0 B. So that makes it 4 ways of dealing with B's. That's all contributing to the count, right? There is a C. How many ways I can deal with C? 2. Either select or not select C. How many ways I can deal with D? 2 ways. In how many ways can I deal with E? Minus 1, right? Because this includes a case in which nothing is selected. Isn't it? This, see, this 5 includes a case in which no A is selected. This 4 includes a case in which no B is selected. No C, no D, no E is selected. That means in this count there is one case in which nothing is selected. But in the given problem, we have to select at least one thing. So exclude from this count, from this product, exclude 1, minus 1. This minus 1 would give me the number of cases in which there is at least one selection. Yes or no? Right? N different books and P copies of each. In the next problem, problem 18, there are N different books. There are N different books. Say B1, B2, B3, Bn. These are the N different books. And P copies of each. That means P copies of B1, P copies of B2, P copies of B3, and P copies of Bn. P copies of each. N different books and P copies of each. Of each. Right? And I want to make a selection from them. That means at least one book I want to be able to select.
P plus 1 to the power n minus 1.
Absolutely. The number of ways in which I can deal with P1, B1, P plus 1 ways. Because either I can select 1 B1 or 2 B1s or 3 B1s or P B1s. That's P ways of dealing with or none. So P plus 1 ways of dealing with P1 and P plus 1 ways of dealing with B2 and P plus 1 ways of dealing with Bn. So that makes it P plus 1 to power n. And this includes that one case in which no book is selected. So exclude that case. Huh? Hmm?
That is the copies of the book. There means there are 5 books of the same kind.
Right, right. There is book H.C. Verma. No, never buy that book. P copies of H.C. Verma, P copies of D.C. Pandey, P copies of Cengage, Mechanics Volume 1, etc. Right? That's what I mean. Okay. You got it right now? Okay, one last thing and I'll let you go. Last problem. M men and N monkeys. M men and N monkeys. Always the case. Because amongst the men are also some monkeys. All right. N greater than M. Number of monkeys greater than number of men. In how many ways can a monkey have a master? In how many ways can a monkey have a master? Right? So these are the N monkeys, say A1, A2, A3, AN. These are the N monkeys. And we want to find the number of ways in which monkeys could have masters. Monkeys could have masters. Now, look. See, we will assign monkeys to masters, not masters to monkeys. Remember this, right? So let's say this monkey, call him A1. All right. Hey, yaar, ससुरे. When I started permutation combination, I said, let's stay within the jurisdiction of rational thinking. I mean, we will, you could theoretically, yes, theoretically it's possible. Theoretically possible, but normally not the case. Now, right, he said it right. See, I told you, with the current day technology, Kushal, remember the current day technology funda that I told you? When I was teaching you rudiments of functions? Right? One father, two sons, all right. But one son? Let's. All right. Stop it. So, N monkeys, and we want to assign monkeys to masters. Okay? We will assume that a monkey has one master. All right? So, monkey A1 can be assigned to any one of the M masters. Amongst these, M men are the M masters. Does not mean that, if a certain man is the master of a certain monkey, he can't be the master of another monkey. Right? A father could have had multiple sons. That's exactly the same. Who knows it better than you? No one knows it better than you. Now, all right, let's give it the finishing touch. So, the first monkey could be assigned to any one of the M masters. The second monkey could also be assigned to any one of the M masters. The third monkey could also be assigned to any one of the M masters. If this guy is the master of a certain monkey, he could also be the master of another monkey. The nth monkey could also be assigned to any one of the M masters. So this into this into this into this, that makes it M to power N. Now this brings us to the conclusion of this class just before pujas. Do enjoy your pujas, but when you come back, there is going to be a work power energy test hanging over you. Right? Huh? Huh? Right. it's not going to be a